Alright, welcome to Engineering 270, Lecture 2A. So we want to start looking at the assembly language way of describing things that we want the processor to do. We've said that the main thing that happens inside the CPU is a fetch, decode, execute cycle. We only really need to worry for now about the execute phase. What does it mean when we talk about executing an instruction? And there's various instructions and various ways that we can modify these instructions, but a general way to think about assembly language programming is to think of two criteria that we need to specify. The first is, what do we want to do? And the second is, to what do we do it? For example, we want to increment the contents of some memory location. So we can think of this as a verb, if we think in terms of language. This is the action that we're trying to perform. And this is what we think of as an object. It's the thing to which we perform that action. For example, increment memory location hex 20. So this is the verb, this is the action, increment, and this is the thing that we're incrementing, memory location 20. Now the computer sciencey sounding terms for this are opcode and operand. So the opcode in this case would be to increment, and the operand would be memory location 20. And so most of our instructions are going to be specified by this pair, opcode followed by operand. We want to do something, and we need to say what we want to do that something to. Alright, so if we think in terms of opcode and operand, specifying an assembly language instruction becomes much simpler. Now, if you look in the datasheet summary from Canvas, and you find table 20-1, you'll see a description of the different types of instructions that are available: byte-oriented, bit-oriented, literal, control. We're going to talk about the byte-oriented instructions. This is what we're going to look at for now. And byte-oriented instructions look like this. They're specified by 16 bits, and some of those bits specify an opcode. That's these first 6 bits. These last 8 bits, this is going to be an operand. And for now, we're not going to worry about the D and A bits. We'll talk about D in a little bit and A much later. But basically, this is the action we want to perform, and this is the location that we want to perform that action on. Now, table 20-1 shows you all of the different opcodes that are available. For example, if we want to increment a file register, we can say INCF, that's the opcode, and we can specify what we want to increment, the file register. So all of our variables are going to be basically locations in memory. These are called file registers. And there's roughly 256 file registers that we can work with, and they're identified by their address going from hex 0 to hex FF. So this is 0 decimal, this is 255 decimal. So 256 bytes of data that we can manipulate, 256 possible operands. There's a few others, but we'll talk about that later. General purpose variables, 256 of them that are available. And the combination of opcode and operand gives us a unique instruction. Alright, so we have file registers, 256 of those. So suppose we want to increment memory location 20. Here's how we would write that in assembly language. Increment file register x20. And if we make a semicolon in our assembly language code, everything after that semicolon is a comment. So we can put a comment here which says what we're doing in this instruction. So this is not the kind of comment you want to write, because this is just going to explain what this instruction means. But let me do that for the sake of illustrating this. So if we want to refer to the contents of memory location 20, here's one way to do that. We can write hex 20, but put it inside brackets. And this is a way of saying the contents of memory location 20. So read the contents of memory location 20 add 1, and then write that back into memory location 20. That's what this instruction does. And it's a read, modify, write. Read this location, modify it by adding 1, and then write it into memory location 20. So read, modify, write. That's our life. And we can increment an instruction. If we wanted to subtract 1, we could say decrement file x20. We could say clear file register x20. And all these instructions you can find in this table. DECF, that's a decrement. CLRF, that's a clear. COMF, that's a complement. In other words, change all the 1s to 0s and the 0s to 1s. So these are all valid assembly language instructions. Well, so far so good. But a lot of times what we're going to want to do is do something to more than one particular operand. For example, we might have 2 locations in memory, x20 and x21, and we want to say add the contents of memory location 20 and the contents of memory location 21 and save the sum back in memory location 21. This is the 20. Well, our add instruction, add WF, lets us add the W register with a file register. We haven't said what the W register is yet, but there's no way to add 2 arbitrary file registers. We can't add locations 20 and 21 together. So the W register is a special register that we can use for temporary storage. And when we code an instruction, when we write assembly language for an instruction, we have an option of saying where do we want the result to be written to. Remember, we're doing a read, modify, write. Well, typically if we read location 20, modify it, and then write back the result, we're going to write it back into memory location 20. But we can choose to write the result instead into this temporary location called W register. So for example, if I say increment file register x20, but then I say comma 0 afterwards, this means take the contents of location 20 plus 1 and write that, not back into location 20, but into the W register. So read from here, modify it, but then write the result somewhere else. Alright, well that's useful because we have instructions like add WF, which says add the W register to a file register. And so if we take the W register and we add a file register to it, we can load the contents of some other file register into W and then add that to another file register. So here's what we could do. We want to add the contents of 20 and 21 together. Let's copy the contents of 20 to the W register, and then let's take the W register plus the contents of memory location 21 and write that to memory location 21. And this will take 20 and 21, add them together, store it in 21. So we want to be comfortable moving things back and forth between the W register and file registers, and there's a pair of instructions that will let us do this. The first is move WF, and this takes a single operand, which is the file register, and this says copy the W register into the specified file register. The other is move F file register, comma 0, and this says take the contents of the specified file register, copy to the W register. So these 2 instructions are going to get used a lot. And they have a very different structure. This is move WF followed by, say, 0x20. This is move F 0x20, comma 0. Totally different structure to these 2 instructions. That's okay. Details are going to be critical in what we're doing in assembly language. Alright, so here's how we can move things back and forth between file registers and the W register. So now, if we wanted to do this, add 20 and 21, store the result in 20, here's what we could do. We could say move F x20, comma 0. And that says take the contents of memory location 20, copy to the W register. And then we could say add WF x21. And that says take the W register, which is hex 20's contents, add contents of location 21, and store the result in hex 21. Alright, now suppose we wanted to say take the contents of 20 and 21 and save that into location 20. We can't start off the way we did up here. This is going to put 20 into the W register, and then we can add that to 21, but we only have two choices. We can store the result in location 21, since that's where we read it from, or we could say comma 0 and store the result back in the W register. So in this case, we actually want to do things in a slightly different order. We'd want to say move x21 into the W register, and then add the W register to location 20 and store the result back in 20. Alright, let's look at a third example. Suppose what we want to do is take the contents of two file registers, add them, and store the sum in a third file register. So take the contents of location 20 and 21 and store that into location 30. Well, we can move file register 20 into the W register. Take the W register, add it to the contents of location 21. So now we've computed this sum. But we want to store that sum in location 30. Well, we can't store it in location 30 with this instruction. We can either store it in location 21, or we can store it in the W register. We don't want to change the contents of location 21, so let's put a comma 0 over here. So now what we've done is set W reg equal to the sum of memory locations 20 and 21. And now we can copy the W register into memory location 30, and we're done. So just adding two file registers and storing the sum somewhere takes 3 instructions in this case. This is pretty typical, right? We're going to see multiple instructions required to do seemingly simple operations. Now, on a complex instruction set computer, this might be a single instruction, one opcode followed by 3 operands. On our PIC processor, which is a reduced instruction set computer, we've got 3 different instructions we have to do in sequence in order to accomplish this seemingly simple task. All right, so the W register is going to be very important, and remember, most of our instructions, if we put this comma 0 at the end, it says write the result into the W register. If we don't put anything here, or if we say comma 1, it says write the result into the file register. And you can see this in table 20-1. For example, add WF takes a file register, comma, and then it takes something called D. D is the destination bit. And if you look up here for these byte-oriented instructions, if D is 0, the destination is the W register. If D is 1, the destination is the file register. So any of these instructions that have a D specified, we can put a comma 0 or a comma 1 after the file register and control where the result of the operation gets written to.